changed and deformed because of earthquakes, and also how the landscape changes through time. And so I'm going to talk to you about how we study earthquakes, some of the things that we use to understand where the faults are, some of the questions that we ask, and we're going to talk about how we do that from Earth and from space. So as an earthquake geologist, these are some of the most important questions that I ask, and these are the things that we're going to cover today. So first, where are the faults? Earthquakes happen on faults. So in order to figure out where the earthquakes are going to be, we have to figure out where the faults are going to be. We have several different ways that we can do that. One of those is using GPS, or Global Positioning System, or GNSS, depending on where you are. This image over here is what a scientific GPS station looks like. They're very, very accurate, and they measure the motion of the ground in 3 dimensions. The image on the left-hand side is an image from UNAVCO, which is an organization that's a large facility for the National Science Foundation that supports geodesy and geodetic research. Each one of the little dots that you can see, they're very, very tiny. That's a GPS station location. The arrows are showing the direction that the ground is moving, and the length of the arrow is telling you how fast it's moving. So if you look at it carefully, not all these arrows are moving in the same direction, and they're not all moving at the same speed. So why does that matter? Well, we have these 2 GPS positions that are, near each other, and one of them starts to move in relation to the other one. Something has to be happening in between them, right? In this particular case, the ground is expanding. This is what's happening in the basin and range. And so you get these normal faults that are causing some blocks to drop down. So we know where faults are, partially because we know the motions of GPS instruments. You can watch that again really quickly. These are all available on the IRIS website for download. So once we know more or less where the faults are, we can go in with very specific techniques to find exactly where they are. One of those is called LiDAR, or light detection and ranging. And this is an optical remote sensing technology that's used to learn about the surface of the Earth. So you can put this, basically a laser, in the belly of an airplane or on a drone or on a helicopter, and it uses laser light to scan the ground and create a 3-dimensional map of the ground's surface. And this is the kind of laser, not like sharks with laser beams on their heads. It's going to like cut you in half. Not that kind of laser, more like the kind you play with your cat, right? So once we have that, we will get something that looks rather like this. So this is a LiDAR image that was collected by the USGS in Northern California. And the San Andreas Fault is actually running through this picture, but it's really difficult to see. So let me orient you to what you're looking at. This popcorn looking stuff on here, those are trees. The flatter things, this is like fields. You can see a road coming through down here, cuts around that way and continues on. This is a fence, and you can see a barn over here. There's some houses in this area. One of the things that LiDAR allows us to do is take out things in the landscape that make it difficult for us to see the ground. So as the laser is scanning the ground, it works sort of like sunlight filtering through the trees. It'll hit the top of the tree, it'll hit some branches, maybe some leaves on the way down, but eventually it'll hit the ground. So we can filter out all of those laser pulses that didn't hit the ground in order to see the ground surface. This is called virtual deforestation. So now we can see what the ground looks like underneath the trees, which allows us to see exactly where the fault is. Now, this gives us additional information that's great for biologists and other folks, because we can learn a lot about the above ground biomass. We can learn about the canopy height, a lot of things about the trees and other parts of the landscape. So now we know exactly where the faults are because we've scanned them. Now, because we know where they are, we can figure out some of the other questions by looking under the ground. So those questions are, how often are there earthquakes on the faults that we found? How big are those earthquakes? And when will the next earthquakes likely occur? So 2 of those questions are about time. One of them is about magnitude. So we'll talk about both those things. And we're going to talk about it for now in reference to the San Andreas Fault. So here's a picture that I took. I think I took this on the San Andreas Fault in near Parkfield, if you're familiar with that, sort of the central California area. And the fault itself is marked here with the black line. you can see it's really difficult to see when you're standing on the ground. It's one of the reasons LiDAR is so very helpful. So we're going to go to this area. Here's a map of California. This is the sort of central California. We're zooming into this area. This is a LiDAR scan of the San Andreas in this region. And we're going to zoom in again into this little white box. So this very strange colored orange and green thing is the LiDAR image of that area. And it's those strange colors because it's showing us the slope. This is a little stream cutting through, another little stream cutting through, and the San Andreas cuts right through here. That's what caused the offset of the stream. You can see another little jog right there. And if you squint, you can sort of see the lineament that marks the fault surface. These little cuts across are called trenches. So in order to figure out when earthquakes have happened in the past, we dig down inside the fault so that we can look at how the layers were disturbed. This is what those trenches look like from the air. This was taken by Ramon Aerosmith, and he's looking down on the ground using a balloon. This is what they look like from the ground. So we basically use a backhoe to dig the trench, and then you have to clean it up really well. You want the walls to be pretty smooth. We'll go in, we'll take lots of pictures, we block it off so we know exactly what we're doing, and then we map it. You can see my friend Jamie here mapping the walls. And people think, oh my gosh, like when we do this in urban areas, they're like, why are those people sitting in a hole staring at the dirt? That's my happy place. Like I am never happier than when I'm in a trench, although you don't want to be the first one in because there's always rattlesnakes in Southern California. Anyway, so once we do that, we'll take all the photographs back to the lab, and here's a mosaic of those photographs, and then we'll take the mapping that we did in the field and we superimpose that. And what we're looking for here are evidence of earthquakes. So the law of superposition in geology tells us that the oldest layers are going to be on the bottom and younger layers are going to be on the top. The law of original horizontality tells us that most sedimentary rocks are laid down flat. So if they're not flat, that means something has happened. And in this case, that something is earthquakes. So if we just follow, say, this blue line across, this is a particular formation of soil, and you can see it's a piece that drops down. There's another chunk over here, and then there's just a piece that's missing. It continues across. The green is very similar. There's a piece, and then there's just a piece missing. That's the result of motion on the fault due to earthquakes. That was what caused these layers to be disrupted. So in the pictures we're looking at now, there's evidence for 4 different earthquakes. So, okay, we know, oh, the important thing I forgot right here. We also take samples for dating these different layers. And so you may have heard of carbon-14, C14. We can also do optically stimulated luminescence and other ways that you can date these different layers so we can figure out about when these earthquakes happened. So we know there were 4 earthquakes here. We know about when those earthquakes happened. So those are our time pieces, right? Now we need to figure out the magnitude. And in order to do that, we need more trenches along the length of the fault. So the trench we were just looking at would be off of this particular map. Each one of these little dots is showing the location of a paleoseismic trench or a suite of paleoseismic trenches. And what we're looking for in these cases is evidence of the same earthquake in different trenches, because the magnitude of an earthquake is dependent in part upon the length of the fault that breaks. So if you have a short section of the fault that breaks, it's going to be a smaller magnitude earthquake. If the whole southern part of the San Andreas were to break, say from here all the way up, that would be a much, much larger earthquake. And we would see, hopefully, evidence of that earthquake in all of these different trenches. If we don't see that, that tells us something about the behavior of the fault. Maybe we only see earthquakes in these few trenches, and we know that there's some kind of structural complexity here we can suppose that will keep the fault from breaking further down, which means it would be a smaller magnitude earthquake. And so those are some of the complexities that we're working on with these faults in Southern California, is figuring out which of the sections actually rupture together, creating larger magnitude earthquakes, which have the potential to be more damaging. So on to the next question. These earthquakes, we know they're going to happen. So what is the effect that they're going to have on people and infrastructure? We need to take a few steps back in order to think more about this question, because I haven't actually defined for you what an earthquake is yet. So we have the surface of the earth. It's covered by a thin skin of rock called the crust, and that's moving around very slowly in these big puzzle pieces. The places where those come together are the places where we have the most earthquakes. The stress and strain of those plates moving, kind of in a broad sense, is what causes earthquakes. And so we have the stress and strain that's building up inside the earth. Eventually, the rocks will break. When they break, that sends out waves, energy waves in all directions. We feel that as shaking. So the main thing that we think of when we think of earthquakes is the ground shaking. Now, this is a really cool video from UNAVCO that's showing the 2015 earthquake in Nepal, really large earthquake. I think it was 7.8. And this is like a closed caption video of a marketplace in Kathmandu. Inset right here in this white box is the recording of a nearby GPS unit. And so you're going to see the motion of the GPS and the motion of the people experiencing the earthquake. This is why we tell you to not try and run during an earthquake, because you're likely to fall down and hurt yourself. Drop down to the ground, take cover underneath a sturdy object and hold on. Or in the case of these folks, you want to get down on the ground so you're not thrown off your feet, potentially injuring yourself or someone else. But there are other things that can happen with earthquakes, right? Oh, sorry. An important point that I want to point out to people, because this is often a misconception, is that ground shaking isn't the same everywhere. There's three main things that impact what you're going to feel during an earthquake. The first is the magnitude of the earthquake, or the size of the earthquake, the amount of energy that's released. The second thing is your distance from the earthquake, which makes sense. If we think about an earthquake like dropping a pebble in a pond, the waves go out in all directions, and the farther away you are, the smaller the waves are. But the local rock and soil conditions also make a really big difference in what you're going to feel. So this is a map that shows the shaking from the Ridgecrest earthquake that happened in 2019 out in the desert in California. So the star is showing you the epicenter of that earthquake. Red is very, violent or severe shaking. And then as you move into the cooler colors, that's less and less shaking. And the heaviest shaking is right around the epicenter, as we would expect. But there's also a pocket of heavier shaking over here. And if you look, there's pockets of strong shaking separated by areas of not so strong shaking. That's because these areas are the mountains, so that's hard rock. These areas are the valleys, which is soft sand and soil. And that soft sand and soil acts like jello. And so you have basin amplification. You'll shake harder and for a longer period of time just because of what's underneath your feet. Another impact from earthquakes is something called surface rupture. So not every fault actually breaks the surface of the earth. Some faults are blind faults. They're down there, but they don't actually quite break to the surface. So if they do, they can do terrible things, like what happened to this cottage in New Zealand during the Kaikoura earthquake. So the fault came right underneath of it. And when the fault moved and broke the surface, it broke the house in half. And after the 1971 Silmar earthquake in the Southern California area, they passed these laws, and I'm trying to remember exactly what the law is, but it's called the Aquas Priolo Act, where you can't build directly on an active fault trace. Seems like maybe you shouldn't need a law to say that, but indeed you do. So we can no longer build directly on active fault traces because we don't want things to get torn in half. Another interesting effect of earthquakes is something called liquefaction. And so if you've ever been to a beach or to a lake, somewhere where there was soft, sandy soil with a lot of water, and you shake your feet, you know how your feet sort of sink down into the sand and your toes get all wet? That's liquefaction. You're causing liquefaction by vibrating your feet. Well, earthquakes also vibrate the ground. So in places where you have soft sand and soil and a high water table, you can actually create that quicksand effect, or an earthquake can create that quicksand effect on a much broader scale. And so you end up having the earthquake, loose, sandy soil, lots of water, and then anything that's on the surface. Because you have this increase in pore pressure, it causes a decrease in surface stability, and then you can have structures that will sink down into the ground. So the home itself may be fine, not collapsing, but the foundation will be compromised. Landslides are another big issue with earthquakes, especially if you're in obviously mountainous terrain. This was a big problem after the Northridge earthquake that was in the Los Angeles area in 1994. There were more than 9,000 landslides around LA after that earthquake. And so this is a map from the California Geological Survey showing many of those different hazards. So these areas in blue up here, these are areas where you have landslide hazard. The green areas are liquefaction hazard, and these yellow areas with the dotted line in the middle, that's places where you could have surface rupture. And of course, all of these different areas will experience ground shaking during an earthquake to a greater or lesser extent. But this brings up a really interesting point when we're talking about hazards and earthquakes. All of these places have earthquake hazard, but the risk in each of these places is different. And we often conflate hazard and risk. So I like to think of it this way, which is a particularly interesting, being that there's a shark talk coming up on December the 8th. So you can tell them we talked a little bit about sharks. So a hazard is something that has the potential to harm you, like a shark in the water. But if you're not in the water, you actually have a very low risk, because your risk is the likelihood of that hazard causing harm. If you get in the water, the hazard, shark, is still there, but now your risk is far higher. And this is a good place to point out that there is no such thing as a natural disaster. What we have are natural hazards that overlap with vulnerable systems, creating a risk, the risk of a disaster. So natural hazards, we have a good idea of what those are: floods, earthquakes, landslides, hurricanes, snowstorms. Vulnerable systems are things we can actually change. We can't do much about natural hazards themselves, but vulnerable systems, things like our infrastructure and development, our land use, the way we use our natural resources, whether or not our population is prepared and understands the hazards that are confronting them, all of those things can make us vulnerable. Another thing to think about, not every community is going to be able to mitigate, prepare, respond, or recover in the same way. And what often happens is that the people that are most vulnerable are the least able to respond, and they're the ones that suffer the greatest consequences. So disasters do discriminate, particularly when it comes to the vulnerable. So that's the down and dirty, quick version of how we study, or how at least I study, earthquakes on Earth. So now let's move out from California and think a little bit more broadly. So now we're going to think about how you study earthquakes and faults from space. We're going to go to the Himalayas. Come with me to the Himalayas. So about 60 million years ago, there was actually an ocean in between India and Eurasia called the Tethys Sea. And about 53 million years ago, India slammed into Eurasia, and it continues slamming into Eurasia into this day, this very moment, uplifting the Himalayan mountains and creating the Tibetan Plateau. So there we are. There's the Himalayas. I call it the chicken. So if you see its head and its beak right there, and then it's got one of those fancy fluffy-footed chickens, you know? So now you're never going to unsee that. You're welcome. I was working in this area right here. So this is showing one particular type of fault in this origin, or place where these plates are slamming together. These are all strike-slip faults, different kinds of strike-slip faults. I was working and interested in this fault right here called the Karakoram fault. It's a right lateral strike-slip fault, which means the right side, if you're standing on the other side, the one across from you looks like it's moving over to the right, so it slides horizontally for the most part. It's very similar to the San Andreas in that it's the same sense of motion and it's basically the same length. But we don't know very much about the Karakoram fault. We don't really have a good history of earthquakes on that fault. We don't know the magnitude of earthquakes that can happen. So there's a lot of things that we could learn about the Karakoram, which is what I wanted to look at. So we're going to zoom into this little area right here. The other thing I was interested in is this other fault coming in here called the Longmu-Ko fault. What happens when they touch each other? Like what's going on there? That's geologically complex. Like that's just an interesting thing. So here's some maps of that area. And I know there's a lot going on here. What I want you to take away from this is that these geologic maps are not the same. Not the same. There's not a lot of agreement about what the rocks are, what exactly is happening here. And there's a lot of reasons for that. So this is a Google Earth image of that area. My field area is the area in blue. I'd like to point out all those red and orange lines. Those red and orange lines are disputed territories, disputed between China, India, and Pakistan. So very geopolitically tense in this area. Also, the topography is pretty phenomenal. I had done a lot of work in the Andes and I thought I understood, terrain. It's amazing. So just to give you an idea of what that looks like, where this little yellow dot is where I took this picture looking in this direction. If we go a little bit to the south, I loved this area because to me that looked like Mount Crumpet from the Grinch, just like incredibly tall, pointy mountains. And then you continue further over and down. This is the little town of Muglib. And then up here, this is getting closer to K2. K2 is just outside of my field area. And I don't know if you can see it, but right down here, see that little white dot? That's actually a 2-story house. So really, really difficult terrain to get to. I was in fairly good shape. I wasn't climbing up this mountain. The valley here is about 16,000 feet. So not a lot of oxygen in these places. So I'm like, oh my gosh, I'm trying to study this fault. And in order to study and understand the fault, I have to know what the geology is like. But there's not even a good geologic map. And it's not like I can go make a geologic map because I can't climb around in these mountains and map everything. Like, what am I going to do? How am I going to fix this? What am I going to do? And I was talking about this over a few beers with a couple of friends. And my friend Chris Edwards goes, why don't you just use Aster data? I said, what is that? He goes, well, he works on Mars. We map the surface of Mars. We know the mineralogy of Mars by using this satellite. Why don't you just use the Aster satellite? It has the same capabilities. And I was like, teach me. So that's what we did. I used the Aster Satellite, which is a high resolution multispectral imaging system that's aboard the Terra satellite. So this is my NASA overlap. I do have some NASA overlap. And it's used for collecting information about the ground and the atmosphere. I spent all my time trying to get rid of the atmosphere, so that part was annoying, but it tells you a lot about the ground surface. In particular, I was very interested in the 5 bands that it has in the thermal infrared. And you can take these 5 bands and you can stretch them in certain ways so that it amplifies the differences in what you see on the ground. And so if you take that and you stretch it these 3 different ways, you can apply those 3 things and make them into a red, green, blue color image, okay? And so we can take these images from these bands and we can figure out what the rock type is. So I'm just going to quickly go through kind of how we would do that. So every mineral has a spectral signature, has like a fingerprint. And so this is what the fingerprints look like. If you put them in the lab spectrometer, the instrument that measures their fingerprint, this is what calcite looks like. It's pretty flat. This is what muscovite looks like. Quartz has a really cool one. It's got the big dip and then the peak and then another dip and so on with each one of these minerals. So the complex looking ones are from the laboratory instruments, but there's only 5 bands on the Aster data, right? So we have to get rid of a lot of that beautiful richness and only use those 5 bands. So if you do that, calcite looks like a flat line. Muscovite has this sort of shape. Quartz has this shape. So we lose a lot of the complexity, but they still look different enough that we can tell the difference. So that's how we know the minerals, and different minerals are what make up rock. And so we can put different rocks into that same laboratory instrument and we can get the shape of what different rocks look like. So this is what carbonate would look like, what quartz-rich rocks would look like, down here, very ultramafic rocks, etc. Okay, so we're going to take this and then I'm going to apply it to Aster images of that field area. And this is what it looks like. This is one little tiny tile of the Aster images, and this is in false color so that it looks like what we would see if we were looking at it on Google Earth. The resolution is about 90 meters per pixel, so it is a little bit pixelated. This, if we take 3 of those bands, and it doesn't really matter what they are, we will get certain colors for certain rock types. In this case, this sort of peach color is carbonate. And you can see there's some carbonate down here too. And this is the same image, but using a different group of bands that we put together. And in this one, the carbonate is green. You can see the carbonate down here also. So if we do that for the whole area, we can use all these different band stretches. I used the 14, 12, 10 on this one. This is what that looks like. It's kind of pretty, right? Like, I think it looks nice, all the colors. But there's actually a lot of usable data in here just beyond the colors. The colors are helpful, but each one of those pixels has data about what the mineralogy is on the ground. And so if we look in the area where this red square is, you can see there's like a pinky peach up here, and then there's a mottled area that's sort of green and purple. If you zoom into one of those pixels and you look at the fingerprint, that is the shape of the fingerprint from that pixel. And if you zoom into one of these pixels, and in this case, 2 pixels, this is the shape of the fingerprint from those pixels. So we know that those rocks are different, right? But how do we know what those rocks are? Well, there were some places that I really was able to go. I could go to that place, I could touch the rocks and say, this is a limestone, or this is a granite, or this is a volcanic rock. And I had the GPS coordinates for those places. And so I went to those places and I was able to plug that exact GPS coordinate in and pull the fingerprint. So I knew what that rock was, and I could compare the spectra of the place I had not been with the place that I had been. And oh my goodness, it did not come out in this slide, but there's a yellow line right here that looks oh so very similar to that blue line. And I knew that this line down here was a limestone. So I knew this other rock that I couldn't get to was also a limestone, and so on. So I was able to do that over this entire map. And this is the craziness that came out of it. I did it across all spectral bands to look at different types of variability. I compared all of the spectral signatures. It took a really long time, and there were a lot of computer crashes, and I had to learn a lot of coding, which was not my favorite. This was a mess. So then I had to make some decisions about splitting or lumping the rocks together. What do I count as its own unit of rock, and what do I, kind of get rid of? So this is the finished map for what I came up with, showing the different rock types in the area. Okay. Now I could actually start the work that I was interested in, which was looking at the faults. But I didn't like the idea of kind of throwing out all of that complexity. I feel like there's such richness in the data that I wanted to explore that. In particular, I was interested in this area right here. So I ended up mapping this whole thing as one unit, the Ladakh batholith granite. And essentially, this is a mountain range that is the equivalent of Japan. So it was an island arc system that got squished in the middle when India was colliding with Eurasia. But if we look at that particular area, look at all the variability across that batholith that I had just lumped in as one purple unit. Excuse me. So I was interested in seeing if we could tell in the spectral data differences between the dark purple and the light purple. And very helpfully, my colleague Jason Dorsch walked across this thing like he is more power to him. That was amazing. But he had collected samples across this batholith. And so I had hand samples that I could then run through the instrument in the laboratory, and then I could compare them to the spectral resolution. So that was what I did. And what I found was, indeed, those areas were very different. So this is the hand sample from the laboratory degraded to the Aster spectra in black, and then the purple, or whatever that is, pink, those were the pixels of areas within the pink sections we looked at, and the same thing with the purple. So there was enough variability and enough richness in the data that we could tell the difference. So just a kind of a future plans, what amazing things could we do using this? And then, correlating it back to things in the lab. Anyway, so back to the map and the question I was originally trying to ask, which is what happens with the Karakoram fault, shown here in red, and the Long Muko fault, which nobody knew where it went or what was happening. Everybody kind of went, goes over there, it's over there. And so we were like, okay, we have some data. Now we can try and figure this out. And, I said it was really hard to get around. We did a bad thing. Well, we didn't mean to be bad, but we were. There's a bridge right here. It's the highest suspension bridge in the world, and it's always guarded. I'm not sure why. China is over here, and this is India, and up there's Pakistan. I'm not sure why it's guarded, because this is not China, although it's contested. But one day there wasn't a guard, so we just drove across the bridge and went there. So these are like moon rocks, these rocks we got, because nobody can get them because you're not allowed to access that part. That part becomes important. So I was interested in trying to figure out what happened to this fault and how it interacted with this other really big fault. So let's zoom in. Why is this? There we go. We're going to zoom into that little area there and look at it from the ground. So can you see that black and white unit that's crossing way high in the mountains? Let's look at it from a different angle. So this is the Google Earth shot. You can see it cutting across right here. And it actually goes across the river and you can see it on the other side. And I was like, that's interesting. And there's a big geomorphic boundary that you can follow along here. And then I was like, oh, look what we found way over here. It looks so similar with the white and the black over there. I wonder if that's the fault. And so we were able to make it up to the area where this crossed the river. And lo and behold, it was the fault. And we were like, that's amazing. It was incredible because it's very sheared, totally crunched up carbonate rocks and skarn, beautiful fault exposure. So it was like, we found the fault, hooray. And we found the continuation of the fault. And then some other observations that we made as we were driving along this valley allowed us to speculate and figure out what we think is happening. So this is what people kind of arm waved about before for the intersection of those two fault systems. And now we could say, okay, here's the Karakoram fault system. Here's that long Mukho fault system, which is left lateral. And it actually comes in and it curves around and becomes a thrust fault along the mountain front. So right in here. Over here is a normal fault. And a different group that was working there at the same time we were actually found this fault working from the other direction, which was also very helpful. And so one of the questions that people had about this is, why wasn't there a basin here? Because if you look across Tibet, there are a lot of fault intersections that are similar to this, but they all have a lake right along the edge. And so why did this one not? It turns out that the angle of contraction between India slamming into Eurasia means that this is getting zippered closed as it extends outward. And this also tells us something about the mechanism of how India is slamming into Eurasia. So how is the continental crust reacting to that? There have been two end member models that people have been throwing around for a long time. One is that this area of Tibet is just moving out by itself. It's not getting deformed. It's just a rigid block that's moving off to the west or off to the east. The other end member model is the peanut butter and jelly model. And in that case, you have India, which is one piece of bread, and Asia, which is another piece of bread, and Tibet is in the middle, and it's the peanut butter and jelly that got squeezed too hard, and it's just squishing out to the east. So lots of deformation internally. And, all models are wrong and some models are useful. That applies here. We think it's probably somewhere in the middle. You do have some internal deformation of Tibet, but it is also extruding along these really large strike slip faults like the Karakoram and the Altantag. So thanks to all my co-authors on this, Ramon and Kip, Alka Tripathi, and of course, Chris Edwards, who was the one that was like, duh, use the Aster data. So that was very helpful. And my favorite sign from the Indian-Pakistan border, quoting Jimmy Buffett, of all things. Very, very random, very fun. So if anybody needs me, you can find me on social media. Hi to all my Twitter friends, but I'll stop sharing and blathering on and answer any questions.
Awesome. Thank you, Wendy. That was great. And I think the crowd is small enough that we won't go into breakout rooms. We'll just have folks share their questions. So your Twitter friends are most important. And Christy is back. She was here earlier. Questions?
Hi, Larry.
Hi, Larry. I enjoyed your GSR.
Great. I'm glad.
I explained everything. I solved all the problems. Yeah. If only that were true.
Yeah.
Hold on, honey. I have a sad child back there. Oh, very cool. Thank you, Carla.
Okay, we've got a
Aster
question.
data is,
Sorry, it dovetails with a lot of your work, and
Mhm. Yeah, no, that's, I'm gonna check that out. I have clicked on it, so it's open in my browser.
yeah, I meant it for the teachers in the room, but you can check it out too.
Is Aster data available to the public or just through professional connections? So Aster data is publicly available, but it's difficult to process if you don't know what you're doing. You want to say hi? Okay. It can be difficult to process. I did all of my work through an open source software through Arizona State, the Mars Spaceflight Facility called JMars, which is sort of like ArcGIS or any of the other GIS software, but it was developed for use on Mars and it is open source. So it can take in the Aster data, and we do have code. I think it's available. It's ugly, but it's around, and you can process Aster data. So we're not the only group that's done this. People have done it for other things. Francis Cooper did some in Bhutan, I believe. Alka Tripathi Lang has done some. I did another project using that with Nathaniel Bornman. So it's around, and there are how-tos available. Although Aster data is going to be going away soon because the Terra satellite is like on its last legs. I learned that today. I was like, no, not Aster.
Yeah, but I assume it's collected a lot of data that's still going to be there, right?
Oh, petabytes of data.
Yes, yes. Any other questions? I can probably come up with one if I. And there's a link from Carla for the Terra satellite and the Aster data specifically. So a question I have that's, a big juicy one that I like to ask pretty much everybody is, how'd you end up doing this?
That's a good question. It was an accident. Yeah, I was a professional actress. My undergraduate degree is in theater, and I did have a geology major also, but more because I just liked caving and thought geology was cool. And I moved to LA and was acting. And then the Hector Mine earthquake happened. I know some of you already heard the story. Sorry, Larry. The Hector Mine earthquake happened. I was like, that was incredible. Oh my gosh, that was amazing. And I went and volunteered at the USGS Pasadena office. Lucy Jones was the one that hired me when said, you're pretty good at this. You want to work here? And I was like, okay. And I was the outreach and education coordinator for the Southern California Earthquake Hazards Program for about 6 or 7 years, and decided that that was what I was really interested in doing, because it was a good way for me to use all of my skills, talking to people. I really was interested in the research. I felt like I was making a difference talking to people about earthquakes. Like, I have a lot of anxiety issues, and I know what it feels like to be scared and afraid and like lying in bed and worrying. And I would talk to people who were like, wow, I feel so much better now that I know these things about earthquakes. And I was like, oh my gosh, I can actually do this and make a difference in the world. So I went back, got a master's degree and a PhD in earthquake geology. And yeah, so that was how that happened. And I told you how the Aster data happened. That was random. And most things that have turned out to be really cool were sort of accidental like that. You're talking to somebody and you just have that brainwave or that synergy, and you're like, oh, it's a great project. We should work on that. And it works out.
Yes.
Do you want to come sit on my lap?
Yeah, and I will note I have a daughter who is a theater major who's making some science education videos, and there's a link if you want to check it out.
Oh, yay. A theater is dead useful. I'm sure my parents were like, what are we doing here? But it is a very useful thing.
I am not worried about it. She has a good head on her shoulders and will do good things. And Carla, do you want to say a word about the link you just put in there?
Sure. So there is a group, the Earth Science Information Partners. They actually started out their roots are in NASA and NOAA and USGS in trying to get data to be compatible, because these different government organizations were putting out data, but couldn't talk to each other. There's an education committee of this organization that is trying to get Earth science data, such as Aster data, different kinds of data sources into the hands of K-12 teachers. We have these little out to lunch webinars. They're 15 minutes. Dawn has done one for us, 10 minutes 10-minute presentation with 5 minutes Q&A. And you can find the previous ones there, but they're really useful resources for teachers. And if you want to come and join us, I put that there because of the interest in data.
Awesome. Thank you.
So yes, Teresa, can I re-explain? I'm also going to put a link to one of the papers about this. It's open source, so free for anyone. So the Aster data collects lots of different kinds of data, the Aster instrument. One of those is the thermal IR, so the thermal infrared. And the thermal infrared can be used for lots of different things. And one of those things is looking at minerals. And there's some caveats to this because the size of the pixel is really big. So you're averaging over a large area, which is not always ideal, especially if you're looking for small features. You do have to do a lot of masking, get rid of the atmosphere, any of the water, any of the vegetation. But you're looking at the surface. And so you're getting the spectral image of the surface. And like I showed that each one of those minerals has its own fingerprint. And you know how some of them had like a dip and then a peak and then another dip? It just so happens that the thermal IR bands, those are the wavelengths that we're looking at. And the minerals are emitting, they have emissivity, they're emitting light at different wavelengths. And so if it hits in any of those peaks or valleys, it makes it real easy to spot because it gives you a different curve. And so that's how we get the fingerprints. And then we just figure out a way to stretch them to make them look, you know, more different from each other, as different as we can. And then we can apply those three things together, just like your TV, you know, it's red, green, blue, or red RBG, RGB.
Yeah.
You know what I mean?
Yeah,
so you put all those together and it gives you a color spectrum. And that's really just to make it easy for us, because looking at the data that way with just the spectral signature would be really hard. So it's explained more in the link that I just gave you.
Great.
Sorry, I'm not explaining very well. It's been a bit of a long day.
That was good. Other questions? I will just put a couple of links in the chat here. The first link is to donate if you would like to support this kind of programming. PRI is a nonprofit, so any donation is helpful. And if you want to see what's coming up, the link is there for that. And we do have the schedule set through the end of the year, and we'll be posting the spring schedule shortly. And if there aren't any other questions, we'll call it a night. And thank you so much, Wendy. That was wonderful.
Thanks everybody for coming. You guys are amazing.
Wendy, I think I missed your link. Is it there?
Oh, it just went to Larry. Hold on. Everyone. Sorry, Larry. Here we go.
There we go.
Thank you.
Mm-hmm.
Thank
All
you.
right. Well, thanks everybody. I'm going to go put this one to bed.
Yes. Ready.
Good night, friends.
Good night, all. Have a good night, everybody.
Thanks, Don.
Yep. Thank you very much. I owe you a beer. Cheers.
I'm going to take you up on it.